going to solve this differential equation. The first thing we want to try to do is get all of our y's on one side and all of our x's on the other. So one way we could do that is we could do a little cross multiplication. We cross multiply, we've got x squared y to the fifth being multiplied to dy, and that would equal the quantity of 3x plus 2. We attach that to the dx. Now I still don't quite have all my y's on one side, all my x's on the other, so I'm going to take this x squared that I see right here, I'm going to divide that over. That would leave me with y to the fifth dy equal to, I'm going to go ahead and take this x squared and divide through to each of these terms. So I'd have 3x over x squared. If I have 3x over x squared, well, this x divides out with one of the x's down here, and I'm left with 3 over x. And then I'm adding on, it'd be 2 over x squared. Now I'm going to go ahead and rewrite this one as 2x to the negative second. So we've got all of that with our dx attached. Now that I have the y's separated from the x's, we're going to anti-differentiate each side. As I anti-differentiate over here, add 1 to the power of 5, get y to the 6th. Take the reciprocal of 6, which is 1/6, place that in front. That's going to equal, as I anti-differentiate the right-hand side, the reason I left this as 3 over x is because when this x is on the bottom, like we see here, and that x is raised to a power of 1, that's a special antiderivative. What I write at this point is 3 times the natural log of the absolute value of x. I know it's the natural log of the absolute value of x because 1 over x would give me that as an antiderivative. I continue by adding on. I'm going to add 1 to my power here of negative 2, get x to the negative first, take the reciprocal of negative 1, which is still negative 1, multiply that to the 2 in front and get negative 2. So I'm going to switch out this plus sign, make that a minus 2, and now I've taken my antiderivative for the right side. Since I've done that, I need to account for the constant. Now if we don't solve any further, this could be an acceptable equation as an answer. If we'd like to clear out this fraction from over here, we could multiply everything by 6. We'd have y to the 6th equals the 18 times the natural log of the absolute value of x minus 12 times x to the negative first, or if we wanted to, we could rearrange this negative exponent, put that on the bottom, make it 12 over x, but we'd still be adding on a constant here at the end. So we got one more example here of solving differential equations. Same objective as the last one. Want to make sure we got the y's on one side, the x's on the other. So here what I'm going to do is I'm going to multiply everything by dx. If I do that, I'm left with dy equals 7. I'm going to go ahead and raise the root on this one. As I raise this root, it's going to be x to the second raised to the 1/3 power. So that's x to the 2/3 power. Got our dx then at the end since we multiplied that over. This one's a lot nicer than the last one because it's easier to separate the y's and the x's. We're at that point where we've done that, so we can anti-differentiate each side. I can appreciate while I do this that technically there's a 1 sitting right there. So if there's a 1 sitting there, just a constant value, as I take the antiderivative of this side with respect to y, all I'm left with is y. And that equals, over here I'd add 1 to my power of 2/3. I'd have x to the 5/3. Take the reciprocal of 5/3, which is 3/5, multiply that to the 7 in front. You got 21 over 5. Taking my antiderivative on the right side now, so just make sure I add on my c value. And since this is already solved for y, this equation is perfect as an answer.